Hey everybody, welcome to another episode of Gnarly Data Waves. And today we're going to have a very exciting topic in the who, the what, the why of Data Lakehouse table formats. Okay, one of everyone's favorite topics for good reason, because we live in the age of data lakehouses and we need to make a big decision in sort of which format we want to use in our data lakehouses. But before we get started, I just want to remind you all to make sure you pick up an early release copy of Apache Iceberg, the definitive guide, by scanning that QR code. Okay, right now the early release stands around 180 pages. The final manuscript will probably be a 300 and plus pages. So, lots of great Iceberg content. Make sure you scan that, pick up a copy, and start learning about Iceberg today. Okay, also make sure to try out Dremio. Head over to dremio.com, click test drive so that way you can get hands-on with the Dremio environment at no cost, no obligation to run some queries and try things out to see what Dremio has to offer. And make sure to visit Dremio at any event that you may be at, such as Big Data and AI in Paris, Big Data London, both in September, Coalesce by DBT in October over there in San Diego. And me and Dipankar Mazumdar, the developer advocates here at Dremio, will be at Data Day, Texas in Austin in January. Don't miss it. We'll be doing an Iceberg AMA as we gear up for the release of the book. And with no further ado, let's get into the who, the what, and the why of Data Lakehouse table formats. Now, let's just start off by just kind of reminding sort of like what the story is here, because we're talking about Data Lakehouse, because the table formats play a very big role in this particular story of sort of like the transition from data lake to data lakehouse. So once upon a time, you have a data lake, a repository, a storage of all your data, whether it is structured or unstructured. And then basically, because you had sort of a variety of different file types from a variety of different places, just kind of like this hodgepodge of data. Mostly you would use different tools to do primarily read-only analytics, and maybe you would ETL a subset of that data to a data warehouse. But you are in that situation making a copy of the data. And then, so now generally the storage that's coupled with a data warehouse oftentimes comes at a premium. So you're paying more for the storage and then running queries on it with more expensive compute, etc., which may or may not necessarily be the biggest issue in the world. But what is an issue is that no platform is really the answer to every use case, especially with the expansion of use cases the way they've expanded recently. So oftentimes you do need different tools. And if every tool has their own storage layer attached to it, then you're making all sorts of copies. And this creates all sorts of issues with consistency and having to keep these different copies of the data in sync and fresh. So that way, and then also making sure you govern all these copies of the data so that way you don't run into regulatory issues. So ideal world, you have one copy of the data and then all your tools work with that copy of the data. Okay, and this is where the data lakehouse comes in. We want that data lake storage to be sort of that the center of truth, okay, for your data. But we want that data warehouse feel where we're not working with a bunch of files. We're working with tables that I can run SQL against, that I can load into a data frame. You know, that you can do the kind of work you usually would do with a data warehouse without necessarily having to bind yourself to a particular platform and have to have multiple copies to the storage that's attached to every platform. So the idea is you can take your data lake storage, that repository, and add a metadata layer on top of it. And that's where this table format comes into play. It provides the metadata so that way other tools, which include data warehouses, data lakehouse specific tools, databases, any kind of data tool, if it wants to be able to communicate with the data on your data lake, it can do so as a normal database, do so through that table format, which allows all these tools to be able to look at the data in your data lake as if they were tables in a database and give that asset guarantees, give all the benefits you would normally associate with a database or data warehouse. And then, of course, you'd have a catalog in the mix that would sort of help make all the tables you have on your data lake discoverable to all your tools. Okay, so essentially it's the table format that really, an embracing of the table format that takes a data lake and turns it into a data lakehouse and makes the promise of a data lakehouse possible. Okay, now several tools that then make that whole thing much easier to implement. But really sort of like when you suddenly have data lake tables using one of these formats, it's sort of when you now say, hey, I have a data lakehouse. Okay, now there's three different formats in the space. So it's Apache Iceberg, Apache Hudi, and Delta Lake, which are sort of the three big table formats. that will give you that benefit of being able to have this metadata layer that allows engines to interact with your data as tables. Now, each of them takes sort of a different approach to how they track that metadata and enable this better query planning. Because essentially what they're doing is they're providing metadata for engines to be able to plan the query, not from having to go through a bunch of different files, but to use the metadata to determine which files do need to be scanned so they don't have to scan every file every time. Apache Iceberg takes the approach of using a metadata tree. Okay, and you have different sort of categories of metadata. So the catalog will basically tell the engine where the metadata is located, and then from there it'll read metadata files, which include something called a metadata file, which is your high-level table definition of schemas, partitioning schemes, and schemas. Use that to determine what snapshot you're going to query, which would be detailed in a manifest list file, okay, which generally will detail which groups of files or which manifests are part of the snapshot with partition stats. So that way you can start saying, hey, this particular manifest I don't need to scan because it's not within the partition values of this query. Do that partition pruning. Once you've pruned a bunch of manifests, you take the manifests that weren't pruned, and those manifests have listings of individual files with stats on the columns in those files that you can use to do further pruning on, and then you end up with your sort of list of files that you would scan. And the nice thing about Iceberg is that it tries to make things reusable. So by doing things in manifests, okay, instead of just one master listing of files, we're able to reuse manifests from snapshot to snapshot, making the metadata writing from snapshot to snapshot minimal. And that's essentially the deal there. Okay, now Apache Iceberg is a little bit unique in the sense that you don't have to have everything in the same folder. You can use a particular file system catalog, the Hadoop catalog, with Apache Iceberg, and it does keep all the data in one folder, but it doesn't have to be. So typically, if I did look at an Apache Iceberg table that was all in one folder using that Hadoop catalog, I would notice in that folder there's two folders, a data folder and a metadata folder. The data folder be what you expect. It holds the data, which either will be a bunch of files or if the table is partitioned, a bunch of folders for each partition with the data files inside of it. The metadata would contain the three types of metadata we talked before. The metadata files, which are JSON. That's going to detail what the schemas are, how the table is partitioned, what are the different snapshots of the table. And then from there, they'll determine, hey, we need to look at a snapshot, which is a manifest list, which is in an Avro file. And that's going to list all the manifests that make up that snapshot, do some pruning. And once it determines which manifests it should look at, it'll then also find those manifest files, which are also Avro files in that folder, which will list individual files. And then based on the query planning going through that process, it can then go through the data files and scan the data files that are determined to be part of that query. Okay, so the idea is that you're using the metadata to reduce the amount of searching and scanning through here you have to do, which saves a lot of time. Because doing a lot of file listing operations is a lot more expensive than just reading a handful of JSON and Avro files. So to kind of summarize, when scanning a Iceberg table, you always go to the catalog, which will tell you where the metadata for that table is. You'll read that latest metadata file, identify the snapshot you're looking to query. Then you will check the manifest list and narrow down which manifest need to be scanned through partition stats. And then take any remaining manifests, scan those, and start pruning individual files based on column stats in those files. And then scan the remaining files that were determined to be relevant to the query that's being processed. Okay? So that's how Apache Iceberg works. But then there's Apache Hudi. Now, Apache Hudi works a little bit differently. It's all based on a timeline. So everything, all the different types of metadata and files that we're going to talk about, they all generally have a timestamp associated with them. And basically, whenever I query a Hudi table, it's going to establish a timestamp of when this query, of when the table, what timestamp it's trying to query the table at. And then it will compare that timestamp to all the files to determine which files are relevant to reconstructing the table. In this case, so everything is done through a timeline, so that way all sorts of things can be happening at the same time, but you're going to capture the granularity that you necessarily want. So now Hoodie like Delta Lake, do generally have all the files in one folder. So generally what happens is that the folder really just has files if it's unpartitioned, and or partition folders if the table is partitioned. So you would just, so if I were to look in the folder for table A, I'm going to see the partition folders or files. But also in that folder, you're going to find a .hoodie folder, and this is where all the other stuff is found. Okay, and before I get to the Hoodie folder, one thing I want to mention is that generally the way the data files are saved is that you'll have the base file, the actual original data file that's written, and then you'll have a bunch of log files that are associated with it. And each log file documents changes to that file. Okay, depending on what kind of, whether it's a copy on write table or merge on read table. We'll talk more about that a little bit later on. Okay, but basically data files are not just data files, but they're also log files that track changes to those base files. Now, in this Hoodie folder, you'll have sort of three categories of extra stuff. You'll have the Hoodie properties file, which is this basically a listing of all the table's properties. You'll have transactional logs, so essentially transactions that have occurred. So essentially what happens is that, let's say I do a write, first what's going to happen is that once I request the transaction, it's going to create a file with the timestamp of the transaction .requested. Okay, that just means like this transaction is about to start. So that way, if other transactions are happening, they're aware that this is about to happen at this particular timestamp. So that way you don't have two transactions hitting the same exact timestamp, creating, irreconcilable differences in a sense. Okay. And then once that query is actually being processed, they'll change that and swap the .requested to .in-flight. And that just means, okay, there's a transaction that's already claimed this timestamp and it's currently happening. Then once it's complete, it'll then switch it to .commit and then actually write metadata to that file about that particular commit that can then be used for processing the transaction and understanding the state of the table. Then third, there's a metadata folder, okay, inside this .hoodie folder, which has basically several different tables that cover Bloom filters for determining whether certain files contain certain values, column stats for helping figure out, hey, do we need to scan a particular file based on the stats of the columns and stats of the columns, and file listings, which list the individual files that make up the table at a particular state. Okay, and basically, again, what's going to happen is that when you go to read the table, it's going to set that timestamp. And then based on that timestamp, because every data file, every log file, everywhere along all these different files, there are timestamps on when things were created or no longer valid or whatnot. So based on that timestamp, it can see, okay, which data files are relevant, which log files are relevant, because each log file has a timestamp. So anything on that timestamp or earlier will be theoretically relevant to apply when reconstructing the table, because it's always the idea you have to reconstruct sort of this metadata on what the state of the table is, and then you can begin to plan the query. So it'll figure out, hey, these are the files that I need to scan based on the timestamp. Then it will use the file stats to begin eliminating those files. Okay. So again, there's that file listing table in that metadata folder. So it'll use that to kind of determine which files are relevant. Then it will use the column stats table to sit there and say, okay, well, these files aren't relevant because of the query and the values that the query is querying. And then it may use Bloom filters to do further pruning. Okay, but after it determines, hey, these are the files that need to be scanned, it will then, scan those files, reconcile any log files that are relevant, and do the actual scan of the table to execute the query. Okay, so that's how Hoodie works. Then there's Delta Lake. Delta Lake's a lot more like similar to how like Git works. So if you ever use Git for like code, what Git does is that it captures the changes by capturing subtractions and additions of lines of code. Okay, so generally if I change a line of code, what I'm doing is I'm removing one line of code and adding another, okay, to replace that line of code. So in this case, in Delta log, each Delta log file represents one change to the table. So like the very first Delta log is just me adding a bunch of files to the table. And then every commit afterwards, I'm either adding files, subtracting files, if I did deletes, or updated a bunch of files. So now I'm using a different file. And so oftentimes both, because if I'm doing an update, it's going to delete the old version and add the new version. So essentially what would happen is that you can always reconstruct the table based on these Delta logs. And then as you create more Delta logs, you get like latency. So to to avoid that, you can create checkpoints which summarize a batch of delta logs, and to speed up the reconstruction of the table. And okay, so if I were to look at a delta lake table and take a look at the file structure in a folder that has a delta lake table, again, at the top of that folder, I'm going to see either the data files if it's not partitioned, or a bunch of partition folders if it is partitioned with the data files inside them. But in there's going to be a delta log folder, and that delta log folder is what contains all the relevant information. So that's going to include, checkpoint files, which are generally Parquet files, or log files, which are JSON files. And basically the way it'll process them is like this. So essentially what it'll do is, its goal is first to build up two things. I need to rebuild the list of files that make up this table and rebuild the metadata that I can use to prune that list. So each commit generally has a metadata, not just the listing of files that were added and subtracted, but metadata on those files that can then be used. So basically, as it goes from log file to log file, which generally have a number sequence of 1, 2, 3, it's adding files, subtracting files, and then building up sort of this metadata table from the metadata in those files that it'll use after it's reconstructed the list. So it'll say, okay, here's a list of files. Here's my metadata that I've reconstructed. Now let me use the data in here to start saying which files I don't need to scan before I scan anything. And then that's how you'll execute the query. Now, again, if there's a checkpoint, instead of going through each log file, it'll just use a checkpoint. And then, so basically it'll start with all the checkpoints, go as far as it can with the checkpoints. And then if there's any remaining commits, it'll then go through the log files and continue building, reconstructing the table. So again, it starts with the checkpoints, then it goes through the log files. Then it's going to use the stats that it collected along the way to begin doing file pruning or data skipping. And then you scan the files that weren't skipped. Essentially, whatever files are left over get scanned. So essentially, that's how mechanically all three of these formats work. But regardless of which format it is, they're going to give you ACID transactions. So you'll have atomicity, consistency, isolation, durability, and executing updates, inserts, deletes. So you can do all that safely. You can treat your data like it is their database tables. Oftentimes, it's not necessarily the functionality oftentimes that's going to really make the biggest difference in choosing between these three formats, more than sort of the ecosystem, support. There are a couple unique features in some of these formats, but for the most part, they generally are going to have most features the same. They're all going to have schema evolution. So in all of them, you're going to be able to update, what's the name of a column, add new columns, remove a column, rename a column, change the data type of a column, reorder fields. You'll have plenty of different options. You can do row level updates in all of them. And now this does differ a little bit though. Okay, so we're talking about here's a concept called merge on read. Okay, so by default, all three formats, they do copy on write. Okay, because that's better for the fastest reads, but it means slower writes. So imagine this, I have a Parquet file that has 1,000 records in it. I update one record in that file. What it's going to do, it's going to write a new Parquet file, but it's writing all 1,000 records just to update that one record, which takes longer, right? So I'm doing spending a lot more time writing than I would have if I had just written the one new record. Okay, so that's copy on write, but that means the new data file is perfectly what the reader needs, and there's no cost on the read side. Merge on read is there to speed up things on the write side. So what you do is, instead of writing the whole file over again, you generally have some sort of other file that captures the difference, the change. Okay. How they mechanically write these is different between format, but the idea is that there's some sort of separate data structure that captures the change to the table or the change to that data file. And then when you read the table, you would reconcile those changes. So that means the read takes a little bit longer, but you've sped up the write, because I'm only writing one new file with one record instead of writing a new file with 1,000 records. With Apache Iceberg, this merge on read technique is decided at the operation level. So in the table settings of a table, you can determine whether updates, deletes, merges, or all three are copy on write and merge on read. In Hoodie, it's a table level setting. So the table is either copy and write for everything or merge on read for everything. In Delta, they've just recently added this as a new feature called the deletion vectors, which is essentially the same idea. You have this data structure that's capturing what's been deleted from a particular data file, It's a new feature. I don't know if it's fully GA yet, or if there's some other limitations in its current incarnation. But essentially, all three formats have a version of this in some form. Okay, Z-order. Now, all three have a mechanism for Z-order, but this kind of really stirs up a bigger conversation. Because Z-order is just a clustering technique. So the idea is you're sorting your data based on multiple fields, equally weighted. So that way, because the idea is like, I don't search my data based on X, and I don't search my data based on Y. All my queries will always filter based on X and Y. So if that's the case, what I can do is I can say, when I'm writing data files, I can say, hey, in the first batch of files, only files that have X 0 through 50 and Y 0 through 50 should be in this batch of data files. And then, so basically what I'm doing is I'm clustering very similar data based on two fields. So now if I do a query where I say, hey, I'm looking for data only records where X is 25 and Y is 30, well, that would fit into this quadrant. So only the data files were written here would need to be scanned, and all the data files here can be skipped. All the data files here can be skipped. All the data files here can be skipped. Okay. But when it comes to sorting, like rewriting data files, whatnot, that's not necessarily a function of the table format. Okay. So this is where like the waters oftentimes get muddied in discussing these things. The format itself is a specification. It's like, how do you write the metadata? Okay. And on the files that were written. Okay, things like clustering, sorting, compaction, these are operations you do on the data files, and then you would update the metadata. So that's a separate operation than how you write the metadata. Okay, like whether a table is Z-ordered, sorted, these aren't things that are tracked in the metadata. Okay, it's just a matter of how you write the underlying data files. So what Z-order isn't necessarily a feature, but the idea is that like Iceberg has libraries that are used to support using the format. Okay. So now it has a procedure to rewrite data files. And when you rewrite your data files to do things like compaction and sorting, you do have the option of applying a Z-order sort. Okay. Hoodie is a little bit different than the other two because in the open source project, Hoodie, it goes beyond the scope of just a specification. They also provide a service called Delta Streamer, which is this ongoing service you would run. So you'd have to deploy it, run it, maintain it. And what it'll do is it'll run compaction, clustering, sorting of your data files parallel to your ingestion. So under the hood, it's constantly like just rewriting your data files, making sure that everything is sort of optimized under the hood. Does that mean you can't do that in Iceberg? No. The Iceberg project takes a different approach in the sense of they just want to be a specification with support libraries to help other tools support the format. But things like providing a service to do optimization and things like that, they want to leave that up to the ecosystem. So currently, like if you want to have that ongoing optimization of your data, right now you currently have two choices. So it's like dremioarctic. So like that's the dremioarctic catalog. Iceberg tables in there can be set to have automatic optimization on a set schedule. There's also the tabular catalog that offers a similar service. So you have those options. But the idea is that they're not part of the Iceberg project. They're part of the Iceberg ecosystem. Okay, so Iceberg oftentimes leaves the idea of services to the ecosystem and focuses on providing a specification and support libraries. While Hoodie provides a specification and support libraries, but also has a service that's part of the actual project. Okay. Although if you didn't want to have to deploy Delta Streamer on your own, you could use something like a OneHouse, which is a Apache Hudi centric vendor that does provide services. I'm kind of automating a lot of that stuff. And then with Delta Lake, a lot of those features like of optimizing and running and sorting your data files in your Delta Lake tables are oftentimes tied to sort of Databricks' platform. So a lot of times optimization are features of sort of the Databricks version of Spark or Photon, which is another Databricks engine. Some of it can be found in sort of just, a open source version of Spark, Apache Spark, but oftentimes like a lot of those service type things are beyond sort of open source Delta Lake format specification, and there's services that are provided by the Databricks platform. And I don't think there, as far as I'm aware, there are no other vendors that provide sort of optimization services for Delta Lake tables. So it's either basically use Databricks or basically design your own service for your own purposes manually. So there's different approaches to how you kind of provide those maintenance services, and Z order and sorting and clustering data is part of maintenance operations on a table. So again, this is where I think the waters get the muddiest when it comes to talking about the three formats. And it's a matter of just understanding the scope of each project, because all projects have solutions for these things. It's just sort of like, it's on the maintenance and support side oftentimes where it's like people will compare the formats and say, okay, one format that doesn't have this because but when it, because there's that distinction between sort of like the project and the ecosystem. So I just really kind of want to make sure to have that conversation, because I think it's an important one when you're thinking through these. So like Iceberg is very ecosystem centric and leaving a lot to the ecosystem, which is partly why it has such an expansive ecosystem, because it didn't try to answer every question itself, but give the tools for everybody to provide several different answers. Okay. Then there's the whole concept of versioning. And this is another story where like Iceberg has a really compelling story. So basically, there's three ways you can version your data lakehouse currently. You can version your catalog. So that means you capture changes to your catalog. Right now, you can do this with an open source technology called Nessie. And Nessie actually also powers the dremioarctic catalog service. But it allows you to capture versions of your catalog, so that way if you make mistakes on multiple tables, you don't have to roll back each table individually. You can roll back the whole catalog. If you need to isolate transactions across multiple tables, aka multi-table transactions, you can do that. So these are the kind of things that catalog versioning enables, but right now that's only available to Apache Iceberg. Now, the Nessie project can and probably will evolve to be able to use more things than just Iceberg, but right now it's primarily sort of an Iceberg mechanism, although it could probably easily support other formats, but it does need this. There is coordination between sort of the formats. So like in the past, it did try to support Delta Lake, but the Delta Lake project wouldn't accept this pull request that was needed to provide that support. But this is a feature that does exist currently for Iceberg. But again, the way it works is that it's just capturing metadata with a reference to the tables in the catalog. So theoretically, you can track anything, which is pretty nice. So like the possibilities with this technology in the future, as far as tracking not just right now currently tables, Iceberg tables and views and namespaces, but tracking pretty much anything on your data lakehouse is going to be pretty open and interesting. So it's a project I highly recommend keeping an eye on, but right now only available in the Iceberg ecosystem. Table versioning, Iceberg is the only format that actually has natively built-in branching, tagging, and merging into the format itself. Okay, and that's really in large part because of the way its metadata is structured. Okay, the metadata isn't structured as sequentially as the other two. So again, like Hoodie, everything kind of relies on the timestamp, and the timestamp being sort of sequential, and Delta Lake requires like all those log and checkpoint files to sort of be in a sequence for it to rebuild the table, which makes it a little bit more trickier when you're trying to say, okay, hey, let's have branching histories. While Iceberg, the snapshots are just an array inside of the metadata.json file pointing to a particular file. So it can say, okay, well, we have different branches or different namespaces for different branches, and then basically here's the snapshot array for that branch, here's a snapshot array for this branch, and track that much easier. So it can actually do that, and you can create branching paths of snapshots in Apache Iceberg tables to do minor isolation of, generally the way they're created in the table format is they're generally temporary, like you said, an expiration date, and then they expire. So they're more meant for like short-term needs, like a quick ingestion job, not for like longer-term retention. I think you can, but they're not. That wasn't, I don't think, really the intent. But you have that option, and that doesn't require using any particular catalog or anything like that. Then file versioning is the only option that works for all three formats, and that's using a system called Lakehouse. Now, as far as limitations with Lakehouse only works for S3 compatible storage systems. So if you're using like Hadoop, okay, so let's say you have an HDFS cluster, and you decide to use Hoodie or Delta Lake, you just have no versioning options. Because LakeFS, what it does is that it tracks branches to your file system. So it's really versioning the makeup of files in your file system, not the table metadata. But what it does is that it's capturing, it tracks them through the file path. So basically, there's a part of the file path that can be switched, and then basically when you change like main to ETL branch or something like that, in that file path, it will then capture like it'll capture that different environment in the file path. While Nessie generally does everything through SQL, and Iceberg is a mix and match of like Java and SQL. Generally, you can do most of it through SQL and Iceberg, as far as the Iceberg table format. But generally, like the final like merging or pulling of a commit right now currently still has to be done through the Java API. But this runs afoul of the Iceberg spec, because currently the Iceberg spec is based on absolute file paths. So when you have absolute file paths, that makes using LakeFS a little tricky, because what happens is that the absolute file path is captured in the metadata, but if you're using dynamic pathing to capture different environments, you might end up reading files for the wrong environment when you query the table, because the absolute file path is inside the metadata. So what LakeFS did is created their own custom catalog that implements a version of dynamic file pathing for Iceberg. But again, whenever you choose a particular catalog in Iceberg, it does preclude you from using other catalogs. So, if you use Nessie catalog, then you can't use the LakeFS catalog. If you use LakeFS catalog, you can't use the Nessie catalog or the AWS catalog or the Hive catalog. Like the particular catalog choice is sort of like the key mechanism that allows your Iceberg tables to be sort of discoverable by all your tools. So just to understand that, like if you're going to use LakeFS with Iceberg, you would have to use the LakeFS catalog, and you'd want to investigate that the tools that you use support the LakeFS catalog. And if you want to use Nessie or dremioarctic, I mean, I can tell you right off the bat, like dremioarctic, which is powered by Nessie, so it's about Nessie support. Nessie is supported by tools like Dremio, Trino, Spark, Flink. Dremio, Spark, Flink, Trino, Presto, and many more. So that's growing support, and there's a variety of catalogs, to the point. So with Hoodie and Delta Lake, you can use LakeFS just fine, because again, they're purely just file system types. Like they don't necessarily, like basically generally when you want to read a Hoodie or a Delta Lake file, usually you're saying, hey, like this folder is my table, and then you read it. It doesn't necessarily as much depend on a catalog for discoverability and knowing what tables make up your lakehouse. Although again, having that catalog offers other benefits and other flexibilities. Again, like Iceberg being able to have the files be located anywhere, they don't have to be inside the same folder. And that's because the catalog becomes the mechanism. So yes, so that's like the versioning story. If you want to use versioning in your lakehouse. Okay, there's also the partitioning story. So Iceberg has a unique partitioning story where you have partition evolution, which allows you to change the partitioning scheme. So you'll be partitioning by year and then suddenly change to month, but you don't have to rewrite the table. The old data will still be partitioned by year, and any data going forward will be partitioned by month. Okay, so it makes changing the way you're partitioning a much less expensive ordeal. Hidden partitioning is basically Iceberg has all these functions you can use to transform partition values. So for example, if you have a timestamp column, instead of creating a month or year column for partitioning purposes, you just apply the year transformation. And now for partitioning purposes, it'll track the transformed value in the metadata. So in your data, you still just have a timestamp column. You don't have any, so you don't have to store additional columns in your data. So you're saving space in your data files. So less storage. And then it can still prune those files based on the transformed value that's being tracked in the metadata. And at the end of the day, the end user doesn't have to be aware of how the table is partitioned, because there's no extra columns they need to be aware of. If they just basically filter the table based on the timestamp, it's going to know that, oh, okay, well, this table is partitioned based on year, based on that timestamp. So let's apply partitioning. Delta Lake gets here in a slightly different way. It uses a feature called generated columns. So the idea here is you are creating another column. So you are storing physically that additional column. But the idea is that you don't have to create the values. Instead, you're saying, okay, the values in this column are a function of another column. So then when you write those files, it'll it'll compute the value based on the function relationship between that and the original column. And then if you partition based on that generated column, if, like, for example, if I create a month column based on a timestamp column and then partition by that month column, for the end user, if they see me querying by the timestamp, it will be aware that the month column, which is the partition field, is based on the timestamp column and will automatically generate the predicate to take advantage of the partitioning. So you kind of end up in the same place, slightly different approach. You are storing the extra column, but you do get to that same nice, easier form of taking advantage of partitioning. And Hoodie, there isn't much of a special way of partitioning. So partitioning stays the way you would traditionally partition tables, a la Hive tables. But Hoodie basically, with their claim is going to be is you don't necessarily need the extra features because the column stats index can then still prune those files out based on your query. Okay, so again, all three formats keep track of stats on the individual columns in the individual files. So there's always that second layer of data skipping that occurs with all formats beyond just your partitioning. Okay, and then there's also the story of format interop. Okay, so the idea is that we're probably going to live in a reality where basically you're going to be using more than one format at a time. So in that case, what are the different possibilities for me making that a possibility? The one definite way you can do now is just you use an engine that supports multiple formats. So like, for example, if you're using Dremio, you could join a Delta Lake table and an Iceberg table because it can read both. But in the future, there's a couple different projects trying to create methods of being able to translate metadata. Because at the end of the day, all three formats, they're just a metadata layer over the Parquet files. Parquet is Parquet. So at the end of the day, like the same 1,000 Parquet files could have Hoodie metadata, Delta Lake metadata, and Apache Iceberg metadata for reading those same 1,000 Parquet files. Okay, they're not writing a special version of the Parquet files or anything like that. Okay, it's just metadata on top of your data. So in that case, the idea is like, okay, how can we translate the metadata layer so that way those same 1,000 Parquet files can be read by different tooling? So one house is working on a project called One Table that's supposed to allow interop and conversion between the metadata for all three formats. The actual implementation details, I think they said they're going to have like an open repo that people will be able to see. These things aren't necessarily like available yet that I'm aware of, other than the actual like announcement. But definitely sounds like an interesting project. And same thing with like Delta Lake. With Delta Lake 3.0, they came out with this Uno format that's also supposed to eventually promise two-way support between all the formats, but currently only supports Delta to Iceberg. So basically, you write to Delta, and then after it's finished writing the commit to Delta, it'll asynchronously write the same transaction to Iceberg metadata. The catch being is that it's asynchronous. So basically, there's a latency between the two transactions. So there's a possibility if someone's querying the Iceberg metadata, they may not get the freshest data. They might not get as data that is as fresh as the Delta Lake equivalent to the metadata. It batches transactions. So like if several Delta Lake transactions happen at the same time, since only one update of the Iceberg metadata can come in, it'll batch those transactions and write all three transactions as one update to the Iceberg metadata. So you won't have necessarily the same granularity of time travel when you use this feature in its current incarnation. And generally the way it works is you have to use the Databricks Unity catalog, because essentially what it'll do is when you write to Delta Lake tables in your Unity catalog, the Unity catalog exposes a Iceberg catalog that it'll write the metadata to. So that's how that works. But yeah, so bottom line is like table formats are a big deal. Now, when it comes to choosing sort of which format you should use, there's a couple of things you have to think about. But it's not as much about features and performance as you think. Okay, you hear a lot of people say X and Y about performance, and oftentimes, no matter, all of them are generally performant. Okay, and oftentimes when you see different benchmarks, there's a lot of like cherry picking of sort of like which TPCDS queries to run, or what's table settings to ignore or not to ignore. So the only way to really see performance-wise which of these formats may work better for your use case is to literally just try them out. Like try a sample of one of your use cases and see which one performs, because the way their metadata is structured is differently. and will lend itself to different use cases. Two, ask the other big thing you have to think about is ecosystem. What engines do you use? Can they read the format that you want to use? Can they write to the format they want to use? Do you plan on using that tool to write? Okay, to kind of determine sort of like what you need, because at the end of the day, like, it doesn't matter how fast something is, if the tools you want to use that you need for your use cases can't work with it, then probably not the format for you. Okay, so these are the kind of things you have to like assess when you're trying to decide sort of which one is the best one for you. In that, yeah, so hopefully this gave you much more information about sort of like how to think about these three formats, how they work. Again, my name is Alex Merced. I'm a developer advocate here at Dremio. And let's begin the Q&A, and I'll see you all there.
Hey, everybody. Okay, that was a barrel fun, and we got lots of questions coming in, so I got lots of answers for all of you. So we'll just kind of work our way through these. And again, feel free to keep adding more questions as we go along. Always a fun topic, table formats. But first, we have how to create index to make query faster. So bottom line is making queries faster. The general principles are going to be the same regardless of which format they are. Like at the end of the day, nothing is going to change the fact that you want to manage your data. So this means, preventing the small files problem through compaction. Okay, clustering your data, meaning sorting your data in a sensible way across those data files, so that way it doesn't have to read as many data files as possible. So that way the data skipping features of all three formats can better skip files. So bottom line, like that's going to be where you're going to get a really large bang for your buck, because technically the metadata for all three formats are the indexes. They're using the metadata to be able to prune and skip data files to really limit that. Now some of them have more explicit indexes, so kind of like Hoodie has like explicit Bloom filter indexes built into the table format. Apache Iceberg in its Spark libraries does take advantage of Bloom filters inside Parquet files. Like there's different layers of that, but bottom line is that all three formats, essentially what they're doing is they're capturing all that metadata, which basically is indexes on several levels on those files, and is using that data to prune. So the better the files are, meaning fewer larger files with more clustered data, you're going to get better performance out of any of the three formats. That also makes it relevant, and also depending on what kind of jobs you're trying to run. Like if I'm doing a very write heavy workload, then I'm going to care about things like merge on read, because if I'm doing frequent updates and deletes, I might be willing to take a little bit extra latency in my reads to be able to meet my SLAs and my writes. So it also depends on the particular use case and how you want to optimize that. But the general principle always is like you want to have better written files, which will also depend on the engine you're using and the configurations with the engine that you're using and how they write and read. Generally, I would point to, hey, what are the tools I'm using to write my files? And then later on, what tools am I using to run things like compaction and clustering after the fact? And making sure you have configurations that lead into your particular query and workloads. And then any table configurations that basically create the right read-write trade-offs for the particular workloads of that table. Okay, what is the difference between Apache Pymon and Iceberg? Okay, so Apache Pymon is like the newest entry. Essentially, far as I understand it, like I haven't actually read that much about Apache Pymon, but from the understanding I currently have, it basically was a format that was used as part of the Flink project that they're now creating kind of as its own separate thing. Exactly what are the mechanics, and is it truly sort of equivalent to what Apache Iceberg, like is it filling the same need that Iceberg, Delta, and Hoodie are filling? That I still have to kind of look into a little bit more to just kind of make sure I understand, like, hey, this is a Pymon format. What is its use case? Is it the same use case, or is it for like a particular, just like strictly, hey, like I'm doing Flink streaming use case? A little bit more into that. It's but that's sort of like the most recently announced format. Cool. In Iceberg table format, if there are multiple DML operations, can I assume the metadata file increase and causes the reads to slow down? Shouldn't. Okay, at the end of the day, like read performance and write performance is going to be very engine specific. So at the end of the day, like it depends what tool you're using to do those reads and do those writes and how they're going to exactly execute them. But in general, the way it should generally occur with Iceberg is that if I have multiple writes coming in, they should not affect the reads at all, far as that read executing, because they're all accessing the same catalog, and the catalog is going to tell the read, hey, here's the newest snapshot. Okay, so here's his newest snapshot, and basically we're going to go construct the table based on that snapshot, while the writes are writing new snapshots. So they're writing new data files and writing new metadata that has nothing to do with what the read is reading. Now, the read will not capture those new data until that write's completed. So basically they're saying the most freshest data as of the last complete write, what the read's going to see. So at the end of the day, they're not going to kind of interfere with each other. The only time like you might have extra latency is if you have the same compute running the same read and write. Like if I have several different transactions being run by the same compute, well, it doesn't matter if they're read or writes, they're all taking up processing power, taking up threads, using up processors that another query can be using. So it also depends on sort of like how are you allocating that compute with the tool that you're using. But based on just say, hey, we're just assuming like, hey, we have just two different operations operating on the same metadata, with each of them with their own set of compute, like there should be no interference. There should be no effect on each other. And that should generally go for the most part, all three formats. Because again, reads, you're only reading existing data files, writes, you're writing new stuff. So there's generally not going to be really a collision. Cool. Once an Iceberg table format is created by an engine like Dremio, then only by using Dremio catalog, we can consume the data. Nope. Okay, so the beauty of all these formats is that once you write it to that format, you can read it with other tools. So if I were to do a create table statement in Dremio, I could go open up whatever catalog I'm using, and DremioArctic isn't the only catalog you can use with Dremio. So if I can create Iceberg tables in Dremio using Hive catalog, using AWS Glue catalog, using the Hadoop catalog, which just means the file system catalog. So DremioArctic is just one choice, and it's just one choice that gives you extra features like the Git-like versioning, the automatic table optimization, but you don't have to use that. And Dremio's catalog support is continuing to expand. So basically, as the roadmap continues moving forward, Dremio will support all catalogs. And you'll be able to run create table statements against all catalogs and read data you've written from other engines from all catalogs. But basically, if I write a table to AWS Glue using Dremio, I can open it up in Spark and vice versa. So bottom line is like the beauty of having a specification, the Iceberg format allows for that interoperability. And same thing with like Delta Lake. If I have a Delta Lake table that I opened up and I created in Spark, I can read it in Dremio. At the end of the day, the format creates sort of that standard rule book for different tools to play for the most part within the bounds of the open source part. We'll get into that. But yes, so what does matter when it comes to a catalog is whether the tool you're using currently has the ability to read or communicate with that catalog, because each catalog could be a different mechanism. Sort of in the long run, like that's where like the sort of like the REST API spec. So basically in the Iceberg project, there's this thing called REST catalog. And what REST catalog is the idea is to try to create like a universal way of talking to catalog. So that way you don't have to worry about, hey, does this tool support that catalog? Long as Y catalog supports that REST API spec, then technically any tool that supports a spec can talk to that catalog kind of thing. So right now, there's I think only like 2 catalogs that do that. So that's gonna be like the tabular catalog, and the Unity catalog is using that to expose those Delta Lake 3.0 Iceberg metadata. But you're gonna see like a lot of these sort of open. You're gonna see a lot of coalescing around these open options like Nessie and the REST catalog. Okay. Can clustering be done on multiple table columns? Yeah, I mean, generally, if you do, well, it depends on the format, it depends on the exact libraries of those formats and exactly how you execute it. That level of detail, like I'm a little bit more familiar with how it's done in Iceberg. So in Iceberg, you would use, when you do compaction using the rewrite data files procedure, you can actually specify like, hey, sort by this field first, sort by this field second. And if you want to do them equal weighted, that's when you would use Z order. But you can do that, and I assume that Delta Lake and Apache Hudi have the ability to configure similarly. Like they both have the ability to do Z order clustering. So I imagine just normal sort clustering with multiple fields should definitely be supported. So that shouldn't be a total order. Again, and just like how you would do it, like with Hoodie, you're probably going to use a Delta streamer to configure that. In Apache Iceberg, you can either do it yourself by using those Spark procedures or Dremio with its optimize command. And or you can have it automatically done using a service like DremioArctic that'll just kind of do it in the background for you for Iceberg. Okay, what is the best way to, let's see, what is the best way to load incremental data into Iceberg tables? Can you please let us know the tools Dremio built in options like this? Okay, so this is not a Dremio specific answer. So Iceberg recently added CDC support. So essentially what you can do is that if you want to capture like the change in an Iceberg table, there's a procedure you can now run that creates a change log file that is essentially like a table of all the changes. So essentially what you would do is, if you just wanted to update a table based on the changes, you would take the original table, run that CDC procedure on that would create the change log, and then you would run like a merge into statement. Then you say, okay, hey, if it's an update, update that record. If it's a delete, delete that record. You know, if it's a new record, insert that record. And basically you would just basically do a merge into and create the right clauses based on this additional column it has that states what type of operation it is. If you take a look at the Apache Iceberg documentation, they show you like what that table looks like. And then when the Apache Iceberg book drops, there's actually going to be a pretty good example of that. That will really illustrate how that works. But that's sort of the engine tool agnostic way of doing it. Now, as far as like Dremio specific features with incremental, Dremio just introduced last week incremental reflections. So reflections are a feature that Dremio has. Think of it as like materialized views on steroids, or as automated data pipelines in a sense. There's different ways of thinking about it. I'm actually, next week's presentation is specifically on this topic of reflections. But if you create reflections on an Apache Iceberg table, you can actually get incremental updates to those materializations. So essentially, if you have frequently updated tables that need materializations for acceleration purposes, usually a challenge is like, how do I keep those materializations in sync? But with Iceberg tables, that's less of a problem because it can capture those changes and then make almost real-time incremental changes based on the changes to the original table. So, you know, cool stuff, really, really cool stuff. Especially, I definitely recommend coming next week to hear the reflections presentation, because I'm going to get really deep into that. And the reflection technology is basically like a really killer thing that people are really sleeping on, that has really profound implications. Okay, so we got some more questions in the chat. So let's see here. We already talked about that. Okay, Q. Iceberg fans often say Databricks maintains control over Delta Lake, even though it's open source under the Linux Foundation. Have you seen any empirical objective evidence of this? Okay, so let's talk about this. Okay, so now, first let's just talk about like sort of like the difference. So like there's the whole like actually no, first let me just talk about like what does it mean, in a sense, like what do we mean by like control over the issue. So basically the issue here, it's not necessarily an issue. Again, it's just like, it's something to be aware of, depending on sort of why would you care, is because a project that's not necessarily as controlled by one particular entity, you know, then it doesn't like live and die by that entity. So like what happens if like Databricks is not here tomorrow? What happens to the Delta Lake format? It's sort of like the question. Okay, there's no one company you can say that when it comes to Apache Hudi or Apache Iceberg. Like the projects will go on because there's so many people who are involved in them that have nothing to do with each other. And that's actually part of the requirements of being an Apache Iceberg project. Apache Iceberg has very strict rules about sort of like the makeup of the PMC, the people who the project, the committers, basically the board. And they have all sorts of rules about sort of like the making sure that it's an independent project, that it's being independently run and transparently run. So generally, like let's say in Iceberg, there's meetings bi-weekly that literally anyone can join. Anyone, and that's where the development is discussed. There's a development email list where proposals are put forth. So nothing's really added to the feature without you having known like ahead of time. Okay, so basically you can be anyone in the community and you know, okay, hey, there's this feature that's just gotten a proposal in, and maybe 6 months down the line that's going to be added, but you know well ahead of time. There's no surprises. Okay, with Delta Lake, at least with the core format, again, so basically like there's different repos when it comes to the Delta Lake project. So if you take a look at like the Rust repo, whatnot, there's probably a lot more participation from the community in building up parity of features into those formats. But when it comes to like the core sort of like Delta Lake format, oftentimes features just come out of nowhere. So for example, Delta Lake 3.0, people who are very into the Delta Lake community were not aware that announcement was going to happen. Okay, so generally like in an open, that shouldn't happen in a real like open source project, because generally like if you're going to add a feature, a proposal should have been made, there should have been a public discussion about the proposal, you know, people vetted what the implementation is going to look like, and it takes time to actually get to that final result because it's an open deliberative process. While that uniformat feature just kind of dropped out of nowhere because it was kind of kept internal and then just added to the format and announced. So is that a bad or a good thing? Again, that's not the point. The point is just like it's a tangible difference in sort of how it's governed, for better or for worse. Now, it's understandable why that's the case, because again, the Delta Lake format was built in large part and is really interwoven into the Databricks platform. So if they were to lose too much control of the project, that would definitely bottleneck their ability to sort of continue building their platform. So I can understand that from like a, like a business perspective. So it's not necessarily like, I don't think, like, I wouldn't say like there's like a lot of times when people are like, oh, it's like it's not open, and it's like out of some sort of malicious thing. It's just like, but when you take a look at it, like it's understandable. But I mean, you can see that, like, for example, the people who are on like the board of like the Delta Lake project, they used to be listed on the repository, the GitHub repository. No longer is, last I checked. And then when you find the commit, you can actually find like the GitHub commit when it was removed, and everyone who was on the committee were all Databricks employees again. And then another example is I every couple months I'll go through the list of committers to each repo and create like a percentage, like, okay, the percentage of people who committed to this project are from this company. And with Databricks is over 80%. Like if you just get the raw data from GitHub, it wouldn't look like that right off the bat, because a lot of Databricks employees don't list their company in their GitHub profiles. So you have to do, usually you can catch it, like they put like DB in their GitHub username, or you'll find it in the email. But once you aggregate those stats, it's like well over 80% of the people who contribute to Delta Lake are to the core project. Again, not talking about like the other repos, Rust. Those, again, but that core project is really what dictates the direction of the format. That is generally like mostly Databricks employees. But again, bad or good, that's not the point. It's just like it's a material distinction that people should be aware of when they're thinking about, okay, what is the ecosystem for this format? That may influence their decision as far as they want to make that long-term commitment and say, hey, I'm going to hitch the future of my company to this format. Because oftentimes with Delta Lake, it has lots of features, lots of really cool stuff, but you are essentially, making a commitment to Databricks in a sense, in some ways. Okay, let's see what other questions are coming in. Grafana visualization does not have a Dremio data source. Is Dremio going to build data source plugin for the same? We're constantly trying to build from a Dremio point of view, so a little bit less on the format side, but Dremio is always constantly trying to build integrations or make integrations and partner up with companies that have as integrations as many tools as possible. So what I would do is, if you're using Dremio and a Grafana, a Grafana integration is something that's important to you, talk about that with your SA you're basically the people you're working with at Dremio, because they're going to be the people who can advocate to the product team to see where things get put on the roadmap, because there's a lot of really cool stuff on the roadmap. I can say that. So a lot of things to be excited about, but of course, there's also a lot to go around. So make sure you make the things you need vocal to your reps at Dremio, and that way we can always be making sure we address what you need. Cool. I think that's pretty much all the questions. But at the end of the day, like, there's 3 formats. They all do a great job of providing ACID transactions, time travel, basically making your data lake work like a database. Okay, they're all good. Okay, this is not about like, hey, one format doesn't work well or doesn't. They all work well. Okay, but the thing is that the question is, what tools do you use, okay, to read and write your data on your data lake? Because that's going to matter, the ecosystem. Okay. 2, okay, well, I mean, and that's also going to be how you want to measure performance, because seeing performance benchmarks in a tool that isn't the tool that you write in isn't going to be very helpful. So you got to be very discerning when you take a look at like people talking about performance of these formats. You really want to run your workloads with the tools that you use, so that you can really see how this is going to be for your data lake, for your data lake house. But hopefully this gives you a better idea of how all 3 of them work. It's kind of like the differences, the computer differences, like, and then all of them are pretty easy enough to just try out. Like, at this point, like, they're all pretty easy to get started up with, and just spin up a couple Docker containers on your laptop. They create a little mini data lake house environment. I know I created one tutorial that allows you to spin up a data lake house right there on your laptop and play with Iceberg. I'll share that in the post webinar resources. But aside from that, I think that's it. Again, come back next week. We'll be talking about materialized views and the differences with Dremio's reflections feature, and why the Dremio's reflections feature is so groundbreaking and innovative. And a lot of these recent changes, like reflection recommendations, incremental reflections, reflection hints, what all of this stuff means, and why is it so important to having a really performant data lakehouse. So I'll see you all next week. Have a great day and enjoy.